We have a homework assignment that is due tomorrow. Hopefully people are well underway with that. If you have not started, that should cause you immense panic. And I hope to see you very soon with questions. As mentioned yesterday, I will have a study guide to you by Friday for an exam a week from Friday. In general, the exams in this course are fairly difficult and rigorous. So be thinking as we're going over the associated material that will be on it. The best time to understand it is when we are going over it. Recommendation of asking and clarifying anything that you possibly can to make your life easier. All right, last time we were talking about converting NFAs to DFAs. You're just introducing this idea. And we were getting into some intuition about it so that when we go cover it, it makes a little bit more sense. So we said that the definition of a DFA is really just a relaxed NFA. It's a further restricted. An NFA is a relaxed DFA that allows for some extra things. But you can restrict what is an NFA further, requiring a total function, requiring that there are no lambda transitions, et cetera, and you get the concept of a DFA. We talked about whether it made sense if we have a DFA, if there's an equivalent NFA. Well, since a DFA is a restricted NFA, it's already an NFA. It's just a further restricted NFA, so that made sense. But the converse of if we have an NFA, is there an associated DFA? And the answer was yes, there is always some DFA for a given NFA. But we have to now define going through those restrictions and making sure that we adhere to them. That'll be a sequence of steps that I will introduce momentarily. We ended the day talking about how many states could be in that associated DFA. What was the limit, the ceiling on the number of states that could be there? And I said that it was 2 to the number of states that were in the NFA, because very similarly to the concept of a power set, we could be in some combination of the states of the NFA, given the parallelism that the NFA represents. Given that we could be in some subset of those states, each one of those subsets of states is going to end up being a potential state in the equivalent DFA. If we were to go through this process, would that result in a DFA? And the answer, surprisingly, is yes. Already answered that question. So let's go through an example of the algorithm. Rather than just giving you the algorithm up front, we're going to go through the process with an example. So here is an NFA. And we're going to convert this into an equivalent DFA. Here's how we're going to do it. First question to ask yourself is, what are all of the possible states, the set of states that we could be in when this begins? So obviously we could be in Q0 because that is the starting state. But you can imagine that there is a lambda transition out of the starting state. There is not in this case. But if there could be, then there could be more than just Q0 that we could be in without consuming an input character. We could be in Q0, or we could take a lambda transition. So it's the set of states that we could begin in. In this case, it's just Q0 because there is no lambda transition out of Q0. That's really the only reason you would add something to that set, is that there's a lambda transition out of the initial state. So we're going to copy that over and make it our initial state. Q0 is the initial state of the associated DFA. We are going to go through an iterative process now where we are going to determine what set of states we could get to in the NFA by consuming the set of characters that are in the alphabet in this NFA. So from Q0, where could we get to when we read an A? What are the set of states that we could get to when we read an A? Just Q1? We're going to copy that over. On an A, we get to Q1. And since Q1 is final, In the NFA, Q1 will also be final in the DFA. From Q0 on a B, what are the set of states that we could get to in the NFA? None. So that is the equivalent of the empty set. So we are going to transition on a B to a state that we're going to call the empty set. Whenever you have a state that is the empty set, it's the equivalent of a trap state, as we've talked about with DFAs. So we can immediately just add the edges on an A and a B, everything in the alphabet. So now we've defined both the A and the B transitions out of Q0 and out of our trap state. Now we need to recurse, loop back around and do it for every state that we just made. So for Q1, we actually made a mistake here. Does anyone see the set of states that we could get to from Q0 on an A? We said it was just Q1. Is there anything further? We could get to Q2 because we could get to Q1 and then lambda transition to Q2, right? So this actually is not just Q1. We're going to call this Q1, Q2. Is that are all the places that we could end up. And this is final because at least one of the states that we ended up in was final. All right. So you can think of this as having forked this process in some way, shape, or form. So we have agents in both Q1 and Q2, processes in both Q1 and Q2. So from this state, now we're going to be asking if we were either in Q1 or in Q2, or both in Q1 and in Q2, what are the states that we could get to when we consume an A? So if we're both here and here, if we consume an A here, we get back to Q1, and then lambda transition to Q2, or just get back to Q1. If we're in Q2, we would get nowhere. That process would die. We're going to take the union of those possibilities, and that becomes the destination edge in the DFA. So it's a self-edge because the answer was Q1 and Q2. So on an A, from Q1, Q2, we go to Q1, Q2. Does that make sense? If we're either here or here, we could consume the A and not teleport. We could consume the A and teleport, or we could have a process die off. Union of all of those possibilities, Q1 and Q2, edge from Q1, Q2 to Q1, Q2. How about on a B? From either Q1 or Q2, how could we consume a B and end up somewhere? What are the places we could end up? Back in Q0. So if we're in Q1, we could lambda transition to Q2 and then read the B. If we're in Q2, we could read the B. That gets us back to Q0. And only Q0?
No. Oh, empty set.
Well, we technically could get an empty, we'd only have the empty set if there are no possibilities.
Okay.
If a process dies, that does not mean we need a transition to the empty set. The empty set is only for if there are, the entire set of this leads to nothing. Every single thread will die. That was a great point though. So now that we've terminated, we can see that we have outgoing edges for, this is now a total function for every state. There's an A and a B outgoing edge. Since that is the case, we can terminate this whole process and say this is a complete DFA. The ceiling on the number of states in it is 2 to the number of states in the NFA, but that may not be the case. You don't have to generate all of those states. You just loop this process until you have a total function. If at any point during this you add a new state, then you will have to determine the outgoing edges to that state. We just guarantee termination by the time we have 2 to the number of states in the NFA, number of states in the DFA, because that is all possible combinations of states that you can have. Questions on this process? Just I've kind of gone over it more intuitively than algorithmically. Did the process make sense? Yeah.
If Q2 had an outgoing edge on A, will we have to separate that from Q1, Q2?
Potentially, depends on where it goes. If it went back to Q1, for instance, then we would not have to worry about it because it would still be embedded within this set. But if it went to Q0, then yes, our Q1, Q2 would have an outgoing edge on an A to Q0, Q1, Q2.
What would that look like?
So we would have something like if we just added this transition on an A. So we have to reconsider this Q1, Q2, because now as we consume an A, sorry, this was to Q0, right? It was not to Q1.
Yeah.
Yeah. So let's just do that. Make our life a little easier. So Q0 on an A can still only get us to Q1 or Q2, but now this edge goes away because from Q1 or Q2, reading an A, either read an A, teleport, read an A, or read an A, stay here. So this A edge now goes to a new state, Q0, Q1, Q2. And since at least one of those states is final, this whole state is final. From Q0, Q1, or Q2, we're looping back around. Now we have to create the outgoing edges to Q0, Q1, Q2. What are the subset of states that we could get to on an A? It's a self edge. We can go from Q2 to Q0, adding Q0. From Q0 to Q1, adding Q1, and Q0 to Q1, lambda transition to Q2 to add Q2. There are many other ways to get to any of those, but it just matters that at least one path exists. How about any of them on a B? Is there a different subset of states on a B? Where can we get to from any of these three by consuming a B? Just Q0? Is there any other way to consume a B and end up anywhere else? No. There is no other possibility. We can't get to the trap because it has to be empty. There would have to be no possible place to end up in order to transition to the trap. So this B now actually goes all the way back to Q0. And now we have a total function again. That was a fun exercise. If at any point this quarter, anyone else wants to say, what if we did, please speak up about it. It makes for fun. Make sure that we can further make this make sense. Any questions? We ready to practice this on our own? All right, I think I walk you through this on the slides, but I don't need that for the exam. So considerations, initial state Q0, initial state of the DFA will be Q0. But as mentioned, one of the common mistakes in this process is failing to account for an initial state where there is a lambda transition. Every way that we can think about this, but this should be everything that I've already said.
everything you
already said. And this just walks you through the process. All right, practice problem time. Here's an NFA. Convert this into an equivalent DFA. Anyone need help getting started? So quiet, where's the collaboration?
So from Q0, you go to Q0 Q1. So I need that state. And on again from Q0 Q1, you go either to Q0 Q1 Q2 now. Because it's if you go with the zero. Because it's like it keeps growing. I don't know if that's right, but that's how I think about it. Because in the last example, it kept expanding the node.
Do you think we have an answer?
I don't know.
Maybe.
Maybe.
Let's walk through it. Give myself a little bit of boredom. What's our phase starting state?
Q0.
Straight at Q0. There's no lambda transition anywhere in this, so we don't have to worry about that. From Q0, what are the set of states that we could get to on a zero? We can get to 0 with a self edge or 1. So we need a transition on a 0 to a state that we are going to call Q0, Q1. Is the state final?
Yes.
Yes, because there is at least one of those states in the NFA that is final, so this state should be final. From Q0 on a 1, what are the set of states we can get to? Just Q1? Is that Q0, Q1, or do we need to make a new state for that?
We need to make it a state.
It is a different subset, so it is a different state, yes. So we're going to say that on a 1, we will go to just Q1. Is that state final?
Yes.
Yes, because it is final in the NFA. All right. Looping around, we've made at least one new state, so we need to figure out the outgoing edges to both of those states. Where do we want to start? Any preference?
0 or the 0.
This Q0, Q1?
Yeah.
All right. From Q0 or Q1, or both from Q0 and Q1, you can imagine having two processes, one in each. What are the set of states we could get to on a 0?
Q0 Q1 Q2.
Yeah, from Q0, we could read a 0 and stay in Q0. From Q0, we could read a 0 and go to Q1. From Q1, we could read a 0 and end up in Q2. So it is all three of the states in the NFA. Is that an existing state that we have so far? No. Time to make a new state. On a 0, we will end up in a new state, Q0, Q1, Q2. Is that state final?
Yes.
Yes, at least one of those states is final in the NFA, so it is final in the DFA. All right, from Q0, Q1 on a 1, what are the set of states that we can get to? Q1 or Q2? Is that a state we have so far?
Yeah.
No. So we need to define on a 1, we're going to go to Q1, Q2. Is that state final? Yes, at least one of those states in the NFA is final. So it's final in the DFA. We just keep adding new states. We're gonna go back to Q1. From just Q1, where can we get on a 0? Just Q2. Is that a state we have?
Yeah. No, not in the graph.
No, not yet. So we need to make a new state, Q2, that we go to on a 0. From Q1 on a 1, that also just goes to Q2. So we can add a 1 to this edge. Q2 is not final in the NFA, so it's not final in the DFA. All right, looping back around. 3 states to add outgoing edges to from Q0, Q1, Q2. Where could we get on a 0? Self edge. From Q0, we can go to Q0. From Q0, we can go to Q1. From Q1, we can go to Q2. So this loops on itself on a 0. How about on a 1?
Q1.
Q1, Q2. We can go from 0 to 1. We can go from 1 to 2. We can't have any way of consuming a 1 and ending up in Q0. That does exist in our DFA. So we can add an edge on a 1 to go over to Q1, Q2. From Q1 or Q2, where can we get on a 0? Just Q2? Where can we get on a 1? We could, yeah, consume end up in Q2. We could here either get there from Q1 or get there from Q2, but it's Q2 regardless. From Q2, where can we get? We'll do the easy one first, on a 1 to itself. From Q2, where can we get on a 0?
Empty set.
Nowhere. So that becomes our empty trap state that we haven't made yet, but we still need. So we'll call that empty. We go there on a 0, and by definition, that loops on itself on a 0 or 1. Total function, are there any missing edges? I think this is complete and correct. We can see that we're quite a few more states this time. We went from 3 states to more than 3 states. Does it start to become a little bit more apparent and intuitive why there's a limit to the number of states in the associated DFA as just every possible subset of states that you could be in? Did we get every one? Are there any that we missed here in that all possible subsets?
0, Q2.
Q0, Q2 is missing. Yeah, 2 to the third would be 8. And we have 1, 2, 3, 4, 5, 6, 7 states. The one that is missing is Q0, Q2. There is no way to be in any set of states in the NFA, consume a set of characters and end up in either Q0 and in either Q0 or Q2. So it's not in the associated DFA. So this was a bit more complicated than the last one. Who got close or got it?
I forgot the Q1, Q2, but I got it to the rest of it.
Nice. How do we feel about this process? Does it seem confusing at all? Relatively straightforward? Maybe a show of thumbs. Completely get it. More practice. Don't know what we're doing today. I just woke up. A lot of more practice. As usual, we'll end up powering forward in the class. But as you think that if you'd like a little bit more guidance on this before you do some of them for homework, feel free to stop by office hours and I can get you some extra practice problems and help you walk through them. And again, if my office hours don't work well for your schedule, send me an email. I will find a time that will work. Anyone need anything else from the board? Any further descriptions, any modifications to the problem to see how it would change? Death by NFA to DFA conversion. Poor Jim. All right, so as usual, I have a solution that we can verify on the slides. So as I upload these, feel free to go back over this problem and here are the solution that you should be generating as we go through that process. If you were following along in the book, this is what you would have had to parse. as usual, I like to give you the technical algorithm because this is how things are related usually. I don't know, I prefer the in-class experience myself. All right, that's the end of introductions to NFAs.
It's like they make it complicated on purpose.
It seems like it at times, doesn't
Yeah,
it?
so no one likes
It's
it.
very mathematical. It's a very universal language. That said, you sit there staring at it for a while to try to make it make sense. I spent an entire summer staring at this textbook and reducing it down into this class's form. It took an entire summer, but it was very worth it because I can't imagine delivering this content quite so technically. All right, the next topic we're going to get into is something that's come up a few times as I've been going around and checking people's answers as they've come up with their own DFAs to problems, which is this really overcomplicated? Is this as small as the answer could be, or there's as few states as there could be? And so we're going to introduce the ability to check whether we have the smallest possible DFA to represent a particular language. This is the new hardest thing we've done in the class. So we know that there are many possible DFAs. There are a bunch of right answers to these problems, but you might ask the question, what is the most right answer? Or what is the most memory efficient answer? Just like there are lots of possible algorithms or instantiations of an algorithm, implementations of an algorithm. Some will be a higher order or more computationally complex than others, and you might want or care to implement an algorithm that's in such a way that minimizes time, minimizes memory, minimizes some weighted combination of those two factors. So determining whether one DFA is better than another, in general, we just care about fewer states. Fewer states means that we can accept or reject faster, potentially, and or has less storage space when we digitally represent this state machine. I'll give you an example. The following will be a DFA. The question I have for you is, can it be reduced? There are going to be some obvious reductions and maybe some less so obvious reductions. The question that I'll really have for you is, how many states are in the final answer? Let's see if we can come to a consensus about how many states are in the final answer for a minimal DFA that solves the language that this DFA accepts. What's the obvious one?
Removing Q1, right? Can we do that?
Potentially, but Q5 is the most obvious. There's no way to get to Q5.
Oh, right.
So what is it doing? What is it adding to? Is it adding any potential strings to this language? No, there's absolutely no reason it should be there, and every outgoing edge from it is useless. So get rid of Q5, that south edge to Q5, and the edge from Q5 to Q4. None of that is necessary. So that gets us down to 5 states. Anyone think we can get down to 4 states?
Probably, but
Raise your hand if you think the best answer is 4 or fewer states and not just the 5 states.
Actually,
Anyone think we could get down to 3 states?
but I think we could 4.
Consensus on 4? No one's brave enough to think we can get to 3? We have one person who thinks we might be able to get to 3.
I don't think we can get.
Anyone brave enough to think we can get to 2?
What if this is just like a cell phone?
That would be fun, right? So we can certainly reduce this, but the answer to this is actually 3 states. That is an equivalent DFA to the DFA on the left. Take a second and stare at that and see if you can logic your way from converting the left side to the right side.
Yeah, it makes sense.
So what this is doing is it's combining Q1 and Q2 into one state that is now Q1. And it's combining Q3 and Q4 into one state that we're going to call Q2 as we got rid of Q5. Now the hard part. Imagine that you're a researcher and you have to come up with the algorithm that is going to, in general, convert some DFA into its minimal form. What would you do? How would you do that? What is a general process that could take something like on the left and determine if we could combine some states?
Probably looking at like the input to a state and also what the state is doing within itself. Like we can see that both Q3 and Q4 have the input of 1, and they're both moving the same way. So we know that this state could probably be represented.
Potentially. It depends on if there's any separate way to get there.
What?
Yeah, because from the starting state, we can get there on the same subset of strings. A 0-1 or a 1-1. Both of those have the ability to get to the same subset of states. Yeah, so in a more complicated DFA, it becomes harder to determine with just a small representation of a local section of that DFA, can these be combined, because the difference might propagate farther and farther away in the DFA. That is a great point, though. There's something about these that it looks like their outgoing edges and their incoming edges share something in common. That's a great point. Anyone else have any ideas? If you like thinking this way, there might be a future for you in research or in theoretical computer science. If you don't like thinking this way, this may be the only class you have to take, and then you can forget that theory exists. Just go do something useful for a living that pays money. But I like posing this question before diving into exactly how to do it. Because on one hand, it's worth learning how to do something like this, but the state of the art is thinking about problems that we haven't solved, and then coming up with an algorithm that solves it.
So like you were saying before, you would look at every path leading up to that node, and then by that you would determine. So is that kind of what you were saying?
You actually don't need to. You can look at all paths starting at the current and start to look at where can we get with strings of length 1, strings of length 2, strings of length 3? And it turns out what matters is actually the finality of the states that you end up in as we do this. But we need some way to terminate, because otherwise we're just looking through an infinite number of potential strings as we expand throughout the DFA. So we need some termination condition. Some way to say we can terminate and conclude that we can combine these, or terminate and say that there's a difference. Therefore, these states are both needed. Let's start the process of talking about it. I probably won't have time to go through a large-scale example of this because it takes a little while to draw it out because it's a relatively complicated algorithm. But we're going to first define some terms. We're going to use those terms as we construct this process. The first is the term indistinguishable. We define this on pairs of states. So a pair of states is indistinguishable if and only if from both states, each possible string in the language results in both leading to a final state or both leading to a non-final state. Does that make sense? Yeah, so we would say these two states that are indistinguishable, we're going to read an A, and the transitions out of those states should either both be final or both be non-final. Then we're going to look at on a B, that's going to either both be final or both be non-final. On AA, it's either going to be both final or both non-final. On AB, it's going to be both final or both non-final. If that's true for every possible of the infinite number of strings that are in the language, then they are indistinguishable. So we cannot brute force this because there are an infinite number of strings to consider. But at least it allows us to define the concept of indistinguishable. There's the book version of indistinguishable. We'll say two states are distinguishable if and only if we can find a string W such that from one state we end up in a final state, and in the other we end up in a non-final state. The goal is to determine whether pairs of states are distinguishable or indistinguishable. One of these questions is easy. One of these questions is difficult. Which one is which? Is it easier to show distinguishability or indistinguishability? Distinguishability, why?
For the set of values that you're trying to prove for, or distinguishability, if you can find one difference, they're distinguishable.
Yeah, you're looking for an example or a counterexample, depending on how you're looking at it. And for indistinguishability, we have to show something for everything in an infinite set. Identify one thing, show a property for an infinite number of things. Identifying the one property, the one example, is going to be much easier. So we're going to latch on to, even though what we really want to find are states that are indistinguishable, because those states can be combined, we're going to be attaching ourselves to the easier question, distinguishability. If we could somehow go through a process that showed every state that is possibly distinguishable, then those that remain would be indistinguishable. That's what we're going to do. So the goal of this algorithm is to find and combine all indistinguishable pairs, but we're going to do it through asking about distinguishability, eventually concluding indistinguishability. Questions so far? Does the concept of the algorithm make sense? Kind of the preliminaries of the algorithm? All right. How do we actually go find distinguishable pairs? First thing we need to do is find and remove any inaccessible states. How could we do that algorithmically? We have a DFA. This isn't something you can look at necessarily. This is now a program that you would want to write to say, we want to find and remove inaccessible states. Algorithmically, how could we do that? They're stored as vertices and edges. Is there a graph algorithm or a graph idea that we could use to find and remove inaccessible states?
Isn't it, if, for example, a state has a edge going into it and has no edge coming out of it, and it's not a final state, then we can say that it's. Well, actually, yeah. Or is that state still important?
It could be that we have an island. It's not necessarily just one state, but you could imagine that there is like a two states that can go back and forth between each other, but they're disconnected in some capacity from the initial state. That would not adhere to that definition, but they're still inaccessible. Looking for anything without an incoming edge. So the example that I had for that was we have some initial state that is connected to something, some set of other states, and then we have two states here that oscillate between each other in some capacity. Both of them have an outgoing edge, both of them have an incoming edge, and they're both disconnected from the starting state. Yeah, that's what we want to do. We're going to start at the initial state, and we're going to iterate simple paths. Where can we get from the starting state? Eventually, we only get to states that we have seen so far. Once that process loops and terminates, we don't add any new states that we haven't visited by going through every state that is on our frontier. Iterate, don't add any new states to that. Any state that we haven't gotten to is disconnected. So we can remove those states. Then we're going to look at pairs of states based on their finality. And we're only going to use finality initially on this first step. After that, we're going to be looking at classes. But we're going to start with all pairs of states. If in that pair, one state is final and the other is non-final, we're going to mark that pair as distinguishable. And I'm actually going to not really talk about equivalence classes. This is how I originally described this process, and I find that it's more confusing than not. We're just going to look at this as a table of distinguishability and not based on equivalence classes. So we're going to consider pairs of states. If we were drawing this out in some capacity, you can imagine this as a diagonal table, is the way that I'm going to write it. So we would have something like, if we had Q0, Q1, Q2, and Q3. It doesn't make sense to consider distinguishability between a state and itself. So we don't care about that, or that. Is distinguishability commutative? If Q0 is distinguishable from Q1, what can we conclude about Q1 and Q0? They're distinguishable. So we only need to fill in half of this table. We don't care about the other half. That's why I call it a diagonal table. It is a 2D matrix of these comparisons, but we really only need to care about, we don't care about order. So we can put X's. It doesn't really matter which side you X out. It could be the top half or the bottom half, but we need the states to be different, and we only need to care about them in one direction. So this would be Q0, Q1, Q0, Q2, Q0, Q3, Q1, Q2, Q1, Q3, Q2, Q3. Once we have those answers, we have all pairs of states and their associated distinguishability. We're going to start by just looking at whether the pairs are final or not. So if Q0 is final and Q1 is not, then we would mark them distinguishable. If they have the same finality, either they're both non-final or they're both final, then we cannot make a conclusion yet. We don't know that they're indistinguishable, but we're going to leave it as a question. We don't have evidence yet that they are distinguishable. So that is how we're going to set up the problem. We're going to immediately mark pairs of states with different finality as distinguishable. Anything with the same finality, we don't have evidence yet. And the goal will be to gather all of the necessary evidence that we need to mark everything that could be distinguishable as distinguishable. And I will show you exactly how to do that tomorrow. Office hours starting now for anyone who would like to work on some homework, get some answers to some questions on some homework, or go over anything else from class today. I'll see you shortly for that.